We're going to look at another model that's going to end up being quadratic. And this would be stopping distance versus speed. The faster you're going, the longer it takes you to stop. Assuming you're going to stop as quickly as possible, on typical dry pavement with typical roads, your stopping acceleration is around 6 meters per second squared. Now, you don't need to understand the physics of that. It simply says that the time you require to stop is what you get if you divide your speed by 6 meters over second squared. I'm not going to worry too much about the units. I'm just going to say that what that tells us then is that the time to stop is 1/6 v, provided the time is in seconds and the speed is in meters per second. Okay, I'll also make you a little note that 1 meter per second is approximately 2.3 miles per hour. So if you divide your miles per hour by 2.3, you get something fairly close to your number of meters per second. Okay, so what it comes down to is if big T stands for the time in seconds to stop and V stands for the speed in meters per second, you have the function T equals 1/6 V. Now, given that, I've got a graph set up here. You should pause, sketch a copy of this, and sketch the graph of T equals 1/6 V. And you should probably also make a table of T versus V. Putting a few selected values in. You can do as many as you like. Select reasonable values of V. So, presumably you paused. I'm going to select a few values of V, and I'm going to select them semi-intelligently. One value, of course, is going to be 0, and it takes no time to stop if you're not moving. I could use 1, 2, 3, 4. I get 1/6, 2/6, 3/6, 4/6 of a second. Those are fractions of a second, and those could be relevant to certain situations. But using more common velocities that you might be traveling at and have a need to stop quickly, let's use 5, 10, 15, and 20 meters per second. Okay, 5 meters per second would be 5 times 2.3. That'd be 11.5 miles an hour. 10 meters per second would be 23 miles an hour. 20 meters per second would be 46 miles an hour. We go up to 25, 30, and you're getting up to highway speed. 35, 40 if you really speed. So, but I'm just going to use 5, 10, 15, and 20. Kind of speeds you would have around town or near a town. Okay, so what's the time to stop? Actually, you know, I could be a little more sensible about this. I could spread the speeds out a little more and make them more easy, make them easier to calculate. I could calculate them more easily. So I was going to say there, if I used 6, 12, 18, 24. Okay, so the reason I choose these numbers is I have the 1/6 here, so why not use multiples of 6? We get a perfectly good set of times. We say it takes 1 second if you're moving 6 meters per second, which would be about what? 13.8 miles per hour takes about a second. You're moving about 12 meters per second. That would be 27.6 miles per hour, which is right at the top speed of a human runner. Very few people have run at that speed. Usain Bolt is over that now. Bob Hayes hit that back in the 60s. Okay, 12, so that would be 2 seconds, 3, 4. Clearly, dividing each of these numbers by 6, or taking 1/6 of each of these numbers, gives us these times. So if I want to graph the time versus velocity, I could use the numbers on this table. So I could say, okay, speeds are 6 12, 18, 24. The times are going to be 1, 2, 3, 4 seconds. So I'm going to end up, and I don't have a real good line of perspective on this board, so I didn't get those perfectly aligned. This point should have been a little higher. Let's go ahead and fix that. Okay, let's fudge it. Okay, so now we have our time. Okay, so this is t equals 1/6 v. Now what we're actually after is not the time it takes us to stop, but what is our stopping distance? And to get our stopping distance, we have to multiply the average speed multiplied by the time to stop. Now, average speed, v represents the speed that we're traveling when we start to slow down. Okay, we're going to slow down from speed v to speed 0. So what would our average speed be? If we're going from speed v to speed 0, why don't we just average v and 0? So average speed equals the average of the initial and final speeds so that would be v plus 0 over 2, which is v over 2. So now we want our average speed multiplied by the time to stop to get the stopping distance. I'm going to have to come over here. So the stopping distance equals average speed, which is v over 2, multiplied by the time to stop, which is 1/6 v. And that, of course, then equals v squared over 12. Okay, so this is average speed time to stop and distance before you stop. Now the idea is simple enough. The greater your speed is, the greater your average speed is too, the longer it takes to stop, so that you're multiplying longer time by greater average velocity. So velocity appears twice, and you get a stopping distance that's proportional to the square of velocity. Now there's another wrinkle on this, but you see where we're getting a quadratic function out of this. V squared over 12 is, of course, a very simple quadratic function.